Recent discussions in modern science suggest that time might not be the fundamental framework of reality we once believed. Instead, it could actually be something that emerges from the strange rules of quantum mechanics. This idea shakes up our deepest assumptions and carries huge implications for physics and our understanding of the universe. In this story, we'll dive into what this means, the science behind it, and why it matters so much. For centuries, time was seen as a steady, ever-flowing river, moving from the past through the present and into the future. In classical physics, time was treated as an absolute stage on which events played out, independent of who was watching or what was happening. Sir Isaac Newton famously described time as absolute, true, and mathematical, flowing at the same rate no matter the circumstances. This Newtonian view dominated until the early 20th century, when Albert Einstein revolutionized physics with his theories of relativity. In his special theory of relativity, Einstein showed that time is not universal but relative, depending on the observer's motion. As an object approaches the speed of light, time for that object slows down compared to a stationary observer. This effect, called time dilation, was a radical break from Newton's picture and revealed that time and space are woven together into a four-dimensional structure known as space-time. Einstein's general theory of relativity pushed this even, further proving that gravity is not a force acting at a distance, as Newton thought, but instead the bending of space-time caused by mass and energy. Massive objects like stars and planets warp space-time, and this curvature dictates both how objects move and how time itself flows. For example, time runs slightly faster at the top of a mountain than at sea level because gravity is weaker at higher altitudes. This effect, though tiny, has been measured with highly precise atomic clocks. These aren't just abstract theories, they have real-world applications. GPS satellites orbiting Earth experience both weaker gravity than we do, on the ground and much higher speeds. According to relativity, weaker gravity makes their clocks tick faster, while high speed makes them tick slower. The net result is that satellite clocks run a little faster than clocks on Earth's surface. If this wasn't corrected, GPS calculations would drift by about 10 kilometers every day. To keep navigation accurate, engineers constantly adjust for these relativistic effects. Still, whether in Newton's mechanics or Einstein's relativity, time is treated as a built-in feature of the universe. Absolute in one case, relative in the other. Both assume that time itself is fundamental. But quantum mechanics paints a different picture. Here, time is usually treated as an external parameter, simply a backdrop against which probabilities shift and outcomes unfold. This stands in sharp contrast to relativity, where time is part of space-time and deeply affected by gravity. 1. Norub. The most fascinating aspects of quantum mechanics is entanglement, a state where particles become so deeply linked that the condition of one instantly determines the condition of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and experiments have repeatedly confirmed it. What's even more puzzling is that these correlations seem to happen without any time delay at all, challenging our classical ideas of cause and effect. Our everyday understanding of reality is built on a simple chain of cause and effect, unfolding in time. But recent research suggests something far more surprising. Time itself may actually emerge from quantum entanglement. Back in 1983, physicists Don Page and William Wooters proposed a mechanism to explain this. Their idea was that in an entangled system, one part can serve as a clock, and its correlation with another part creates the sense of time passing. Without entanglement, the universe would look completely static, frozen without any flow. In this view, time is not a basic feature of reality but a byproduct of quantum correlations. This perspective fits neatly with the Wheeler-DeWitt equation in quantum gravity, which is striking because it doesn't even include time. Instead, it describes the quantum state of the universe as a timeless whole. According to this idea, time only appears when we zoom in on subsystems and compare them, reinforcing the notion that time is not fundamental, but something that emerges from the entanglement and interaction of quantum states. If this is true, it challenges two long-standing views: relativity's picture of time as part of space-time, and quantum mechanics' use of time as a fixed background parameter. It suggests that an even deeper theory may exist, one in which space-time itself, and time along with it, emerges from more basic quantum processes. Such a framework could finally bridge the gap between the two great but conflicting pillars of modern physics: general relativity and quantum mechanics. Understanding time as emergent also sparks exciting new possibilities in fields like quantum computing and information theory. If time truly comes from quantum correlations, then by controlling those correlations we might unlock revolutionary ways of processing information, potentially changing technology as we know it. But these ideas don't just affect science, they also strike at our beliefs about reality, causality, and even consciousness. Traditionally, we think of reality as a sequence of events unfolding in time: past, present, and future. Yet if time arises only from quantum correlations, reality may be more like a static block in which all moments exist at once. Our sense of now could simply be a mental construct created by our brains. This view echoes Einstein's relativity, which treats all points in spacetime as equally real, with no universal present. If that's the case, reality might not be as dynamic as it feels. Instead, our perception of flow may be a subjective illusion, shaped by how our minds interact with the universe. This concept of emergent time could be the missing piece in the quest to unify physics. Relativity treats time as flexible and shaped by gravity, while quantum mechanics treats it as an external parameter. Emerging theories like string theory and loop quantum gravity suggest that space-time, and by extension, time, arises from even deeper structures. In string theory, time may come from the vibrational patterns of tiny fundamental strings, seamlessly blending into spacetime. In loop quantum gravity, spacetime is built from discrete chunks, with time emerging from their interactions. And in the Wheeler-DeWitt framework, the universe is described without time at all, with the flow of time only appearing when subsystems interact. All of these approaches point to a major paradigm shift. Time may not be a built-in ingredient of the universe, but rather an emergent feature of a deeper, unified theory. This also opens fascinating questions about human consciousness. Some theories suggest our brains create the sense of time's flow, imposing cause and effect on what may actually be a timeless quantum reality. Neuroscience supports this, showing how the brain stitches together sensory input into a coherent narrative of past, present, and future. This ability, often called mental time travel, is essential for survival, allowing us to predict dangers and plan ahead. But if time is truly an illusion, that raises profound questions about free will and causality. Could our choices be predetermined, with the feeling of freedom just a mental construct? If all moments already exist, then perhaps free will is not what we think it is. The idea of emergent time doesn't just reshape physics, it touches philosophy, technology, and how we view ourselves.